Well, first of all, thank you to the organizers for inviting me. Delighted to be here. Lovely to see such a big crowd, enthusiastic. So, I'm going to talk about some of these hidden laws of life, of this messy world around you, that there's these phenomenal regularities and systematic behaviors that are sort of hidden from our sight. And I want to try to reveal some of that to you. And I want to do it because it's really important to understand how the nature works, how the planet works, how our socioeconomic system works in terms of the huge challenges in the future of the planet. And towards the end of the talk, I will bring up this whole question of singularities and what that might lead to. So the question I'm not going to answer is either, are we sustainable? Or the most fundamental question, how do we achieve a flourishing future of a projected 9 to 11 billion people as an integral part of a life-sustaining Earth system? But those are the questions I want to lead up to, and maybe in the question-answer period we can speculate about some of that. But I'm bringing to it a physics perspective. I'm a physicist, a theoretical physicist, and I want to tell you at the beginning just a little bit about what that means. And I'm going to do it with some help from my non-physics friends, but begin with a quote from a famous physicist named Steven Weinberg, who made this statement, a very pithy statement. Our job in physics is to see things simply, to understand a great many complicated phenomena in a unified way in terms of a few simple principles. And I want to add to that the following, because this is what I'm going to try to get across in the rest of the talk. The search for underlying laws and principles leading to a quantitative, computable, predictive, testable, conceptual framework, and the search for unification and transcendent phenomena, things that transcend the particularities of whatever the thing is that we're looking at. Here's another view of physics. Some of you presumably have heard of Rutherford, but you certainly are familiar with what he introduced to us, this idea of the atom as a kind of mini solar system. And here's what Rutherford said about physics, very arrogant remark. All science is either physics or stamp collecting. And I'm not sure I subscribe to that, but here's a much more important statement that's relevant for tonight. A theory that you can't explain to a bartender is probably no damn good. So that's what I see the challenge tonight. I hope I can get across to you some of these ideas that a person without the technical background can truly understand. I've got one other statement that he made, which I think is important for today, and that is, we've got no money, so we've got to think. So I think that's... So the extraordinary thing about this way of thinking is it's led to all these phenomenal things that we all participate in terms of what science and technology has given us. This way of thinking about fundamental questions, looking for fundamental laws, principles, trying to make it predictive, testable, has led to this extraordinary society we live in, but it has also led to a deep understanding of the cosmos, of the evolution of the universe from the Big Bang. You're all familiar with the idea that we live in this exponentially expanded universe, but we understand in an extraordinary amount of detail in some instances, but certainly in a kind of coarse-grained way, the evolution of the universe from the Big Bang to creating galaxies, to creating planets and the kind of planet we live in and so forth. So that's all come from this way of thinking, which has been fantastic. However, let me skip this. I don't need to do this. You don't need to know that. When we look at our own planet, something extraordinary in contrast to what I said. Whoops, have we lost the... Physics is not working, apparently. Ah, very good. So here we have this extraordinary understanding of the universe and many of the things around us. But on the planet, we have all this junk, all this crap that we've created. And physics has very little to say about much of this, all of this stuff, and especially this stuff. So I'm going to try to scratch the surface of that and try to give you a physics perspective on this and this. So the first thing to understand that all these things are interconnected. Furthermore, that these systems, unlike what we talked about at the very beginning, are highly complex, they're interrelated, they have different scales, they're continually adapting and changing, and we call those complex adaptive systems. And the extraordinary thing is that our planet is more complex than the universe itself, which is kind of a remarkable, we're in an extraordinary singular special place. And so it's kind of interesting to divide what we think about the planet into two pieces. They're, of course, highly interconnected. The biosphere and the anthroposphere, what we've brought to the planet, where we've separated from the biosphere. And also to think of it in terms of simplicity, which is the physics side of things, where we can write the equations, where we can understand the motion of the planets, the cosmos, we can make airplanes and iPhones and all the other wonderful stuff, as distinct from these kind of things, which are, as I say, continually evolving. So this is a question that was posed to Stephen Hawking at the turn of the millennium. Some say that while the 20th century was the century of physics, we are now entering the century of biology. What do you think of this? To which Stephen responded, I think the next century will be the century of complexity. And I think that's the huge challenge that we on the planet, and in particular the scientific community, is facing. How to come to terms with the extraordinary complexity and the continually changing aspects of complex systems. So we're going to talk a little bit about these. And the first thing to recognize is that all these have many levels of organization that all have to be interconnected and interrelated. They all have to act in a coherent, integrated way, whether it's the kind of social organizations we participate in, going from people to companies to urban areas, or from within our own bodies, from the complex molecules up through cells, through organs, to operating as a single body. All of that has to happen in a highly integrated way. And how does that happen? It happens through networks. So a lot of what I'm going to talk about is going to be talking about networks. So you're all familiar with these. We have networks at all kinds of scales. We function basically as networks, but there are also, of course, infrastructural networks that, of course, is part of our general life. But of course, there's also social networks. What's going on here, in fact, is part of a social network. Our interface, exchanging information, and so on. And that social network has all kinds of interesting properties of modularity, meaning we have families and groups and divisions and departments and so on. And first of all, I'm going to talk about the biological networks. And here's what's amazing about these networks, is that the mathematics and physics of these networks leads to extraordinary simplicity underlying the extraordinary complexity of life. So I'm not going to tell you, I'm not going to show you any of the mathematics, obviously, but the idea is very simple, that the these networks have general mathematical and physical properties, and also that the continuous competition inherent in natural selection, in the evolution of organisms, in the competition, has led towards systems becoming optimized, more tending towards being optimized. And that optimization leads to some extraordinary simplicity, such as this. So what is this? This is a graph of the most fundamental quantity of your life, actually, namely, how much food do you need to take in each day to stay alive? That's called your metabolic rate. And what's plotted here on the vertical axis is metabolic rate versus the weight, the body mass of a sequence of animals. And it's plotted logarithmically, meaning I go up by factors of 10, I go up by factors 1, 10, 100, and so forth. And if you plot it that way, that whole structure of thinking in terms of the mathematics and physics of networks leads to this extraordinary simplicity for how metabolic rate scales with size as you increase the size of organisms. And the other aspect of this is that the slope of this is predicted by the theory to be the number 3/4, which I will talk about in a moment, which means that number is less than 1, which means which we call sublinear. And so that slope is less than 1, which means the bigger you get, the less energy is needed per unit gram of tissue or per cell to stay alive. You're increasing the amount of energy that you need as you increase size is less per unit in order to keep it as a system viable. And that is a systematic economy of scale. So that follows from, just let me repeat, from the mathematics and physics of these networks, which are presumed to be optimized by the process of natural selection. The other thing that the theory tells you is that all of these networks are so-called fractals, which means that they just repeat themselves. They just keep repeating themselves, as you can see. So we have this remarkable result. There's this incredible diversity and complexity of nature, all these multiple facets of nature, and yet there are these simple scaling laws that hold not just for this most fundamental of quantity, namely metabolic rate, how much energy you need to stay alive per day, but for almost everything. So I'm just going to flash on a whole bunch of variables. Some are things like the amount of, look at the top right-hand corner, the amount of DNA in your mitochondrion. Some are lifespan. Some are the structure of your brain. I'm not going to tell you what each one of these, doesn't matter. You just see all of them have this very, very simple relationship when you plot them in this way, this logarithmic way, going up by factors of 10, predicted by the theory, and the theory predicts the slope of all those. Here they are. And they're dominated by this number 4. So the number that dominates nature, the biosphere around us, is 4. Not 7, not 21, not other magic numbers. The number is 4. And that 4 has its origins in 2 things. One is the fact that we live in 3 dimensions. That's 3. The +1 is that fractality, that fact that it keeps repeating itself, adds an effective dimension, if you like, to life, so that this number, the number 4, is in a certain sense 3 + 1, 3, the dimension of space we live in, and +1, the optimization being manifested in the fractal nature of these networks. Okay, so there it is. There's that general manifestation. So what I'm going to take you now to, I'm going to continue with this, and I'm going to move very shortly. I'm going to do one or two things still within the biosphere. I'm going to show you that this pattern repeats itself outside of the biosphere, but in the world that we live our daily lives in, namely in cities and companies, and in fact, across the entire planet. So it's sort of wonderful in a way that you see this sort of unity of nature that gets expressed from these very simple scaling laws that are a representation of this evolution of nature. And I just have this quote here from Einstein: "It is a magnificent feeling to recognize the unity of complex phenomena which appear to be things quite apart from the direct visible truth," these hidden laws. So I've already mentioned the bigger the organism, since it's scaling sublinearly, 3/4 less than 1, it means that per cell we have less energy is needed. So your cells are working less hard than your dogs, but you're working harder than your horses. So just to give a sense of that, an elephant is made up of about 10 trillion cells, 10 to the 13th cells. But you could have made those cells into a bunch of mice. And in fact, if you do it, you get about 20,000 mice. So you could have the same biomass being either 20,000 mice or one single elephant. But here's what's extraordinary. A single elephant requires only about 25,000 food calories a day to stay alive. But the 20,000 mice, the equivalent biomass, the same number of cells made up as mice instead of a single elephant, requires 500,000, 500,000 calories. 20 times as much. So that's the extraordinary economy of scale that sweeps across nature from the smallest to the largest. The other aspect is, if less energy is being used per cell, the bigger you are, that means less damage is done. Less damage is being done, the bigger the animal. If less damage is being done to the cell, the longer that cell will live, the longer the organism will live. Therefore, this predicts that bigger animals systematically live longer, following, again, one of these quarter-power scaling laws. Well, you have to do all the mathematics and so on to verify this to be true, but this very simple argument already suggests strongly that you would expect this systematic increase in lifespan, and at the same time, you would expect, you would need less sleep. Why would you need less sleep? Because what is sleep? The reason you sleep is in order to repair your brain, and the damage being done during the day and all the various activities that you do needs to be repaired, and so you shut down the system at night, and that gets repaired. But if you're doing less damage the bigger you are, that then suggests that the bigger you are, the less sleep that you need. A large animal needs less sleep. And I suspect, someone put up their hand if they know how many hours an elephant sleeps a night. No one. How many hours does a mouse sleep at night? No one. We have a young lady down here. How many? No, well, we sleep 8 hours, roughly. So a mouse sleeps about 16, about twice as much. And an elephant only needs 2 or 3. It's all an elephant that sleeps at night, 2 or 3 nights. And a whale 1 to 2. So it just follows from this. It just follows from this very simple scaling law and so forth. So I think I showed data. Yes, here's the data. So I plotted lifespan vertically, the size of the animal horizontally, and these are us. These are mammals, And I don't know if you can see that arrow pointing in the red is that 1/4, 0.24. It's very close to the predicted 1/4. Okay. So this is one of those results. I actually had it on that graph. This is heart rate decreasing with body size, and the slope of this is drawn in as 1/4. It's minus 1/4. Heart rates decrease with size. I already showed you this lifespan increasing with 1/4. That was increasing. I'm going to show up the heart rate decreasing. Now, if I multiply them together, the increase of lifespan with 1/4, when I multiply it by heart rate, is cancelled out by the decrease with minus 1/4. So if I multiply heart rate by lifespan, I should get something that doesn't change with size. It'd be the same for all mammals, whether you're a mouse or an elephant or a human being. And so there's the data. It doesn't. And what is heart rate times lifespan? That's the number of heartbeats in a lifetime. So whether you're a shrew, which sits on the palm of my hand, or a blue whale, which would fit just about inside this building, you would have, roughly speaking, the same number of heartbeats, roughly 1.5 billion. So it's kind of, it has a sort of spirituality to it somehow, that's despite the extraordinary range of size, a shrew to a whale is 10 to the 8th. That's 10 million times bigger a whale than a shrew. Nevertheless, during the lifetime, their hearts beat pretty much the same number of times as 1.5 billion. There it is. Okay, now I decided, fuck it. I'm going to put up one bunch of equations. My God, mathematics is sort of the language of the universe in a way, and somehow we should all speak it. Well, I just wanted to show this. You don't have to. I mean, this is just a joke in a way. But in that box, oops, I'm sorry. Whoops, I have to go back. In that box there is the connection between lifespan, the time that you're awake, divided by the time that you're asleep, raised to some power. Then there's a little formula that connects lifespan to how long you sleep, with a factor of 6 years in here, which is kind of amazing. So there is this intimate connection. This does very well with the data. And I always like to point out that this has been known for over 2,000 years. This is a painting of Thanatos and Hypnos. They were twin brothers. Thanatos is the god of death, Hypnos the god of sleep. They're twin brothers, and in fact, they're both sons of the god of night, Nyx. So this was known to the ancient Greeks, this connection between sleep, maybe not that formula, but certainly this intimate connection between the two. So cradle to grave. So we talked about living, and we just talked a little bit about dying. And by the way, I'm sort of here. I'm ready to go here very soon, actually. But actually, I'm going to go backwards. I want to go grave to cradle, because I want to talk about growth, because that's sort of crucial. So we've all done it. We've all grown. We've all scaled up. So how do you grow? Well, you eat, you metabolize that food, goes through the networks, sends metabolic energy and resources to the cells, to your cells, and at the cellular level, it repairs ones that are damaged and replaces ones that have died, and then it adds new ones. So that's what that says. That's that sort of an equation. Oh, damn it. Sorry, wrong one. There's your metabolic energy, goes to maintain ones that are there, and then adds new ones. So you can write down, you have to put that into mathematics. And so it's sort of a supply-demand equation. There's a supply, goes to maintenance, as I say, and then to growth. But the supply is increasing less than linearly. It's going slower than linearly, but the demand of maintaining is approximately linear. So the sublinear, the one that's going slower than linear, cannot keep up. That's why you stop growing. So you can't, the supply of metabolic energy cannot keep up with the demands of maintenance, and growth ceases and you stop. And there you are. There you are as a mouse, stopped growing. You start growing quickly and then you stop. So this sublinear scaling leads to boundary growth, and this is crucial across the biosphere in terms of its long-term sustainability, that most organisms spend most of their life in a kind of stable configuration. I mean, we may get a bit fat here and there and so on and so forth, but basically we stay in this stable, roughly stable state. Okay. So you can predict the growth curves of any animal. There they are. There's just a bunch of them. And then you can rescale these. I'm just flashing this on. You can rescale these because you have a sort of universal theory of growth, so that if you rescale appropriately, and I'm not going to go into the details of it, but the point I want to emphasize is that by appropriately rescaling, determined by the mathematical theory, everybody follows the same growth curve, roughly. And we know the theory tells you the form of that. And you can see this is just some group of animals. There's birds and fish and mammals on there. And so it's kind of interesting. So if you look through the right lens, everybody is sort of growing, following the same curve and at the same rate. And if you look through the right lens, everybody is living everybody. All organisms are living, roughly speaking, the same length of time, for example, as measured by the number of heartbeats. So it's kind of amusing in a way, slightly depressing, I guess, that tumors obey this too, because they're just part of you. They're just another part. They're like a mini organism, and they fit on this, as do, in fact, insect communities, social insect communities, bees and ants and so on. As a whole, as a complete community, they fit on it. They act essentially as a superorganism. And that will be a little bit of a segue into cities. Okay, so here's a summary of this first part on the biosphere. We're dominated by these 1/4 power scaling laws, which I talked about earlier. They express an economy of scale. The bigger you are, the less you need per capita, the less you need per cell to stay alive. The pace of life, I didn't emphasize this, but life systematically slows. I just showed it via heart rates. Heart rates decrease systematically the bigger you are, following these scaling laws. Times get stretched out, you live longer appropriately, and so forth. Growth is sigmoidal, which simply means you grow quickly and then you stop into a stable configuration, and then you die. And you can explain it all with this kind of network paradigm. Okay, so I now want to move to the Anthroposphere and take this same idea and try to talk about the aspects of the Anthroposphere. So I'm going to start with a photograph taken by a NASA satellite in 1820 of the planet at night. Of course, there weren't NASA satellites, but you could imagine there might have been, and that's what they would have seen. Nothing. The Earth would have been black, wouldn't have seen anything. This is already 20, 30 years after the Industrial Revolution. maybe another 20 years. I don't know if you can see, maybe some people in the front can see maybe a few little bits of light showing. So this is maybe 50 years into the Industrial Revolution. But jump ahead just another 100 years to 1940. I chose 1940 because the year I was born, by the way. 1940, and you can really see these lights. And of course, you jump to today. Phew. So what is it we're looking at? Well, you all know what that is. That's just night lights of cities, basically. It's just the night lights. But actually, it's much more than that, because where do those lights come from? They come from burning fossil fuel almost entirely. So what this really represents is this. That's what's going on, and it's just burning the surface of the planet. This picture, which is kind of pretty and beautiful in a certain way, is just the burning of the surface of the Earth. That's all it is. Just happens to be that it's lighting our cities. Okay, so so we have this extraordinary urbanization that has taken place on the city. You saw, just in my lifetime, it's gone bonkers. So here's some numbers. From now to the mid-century, we're urbanizing well over 1 million people a week. Some people estimate 2 million, which is kind of extraordinary. What does that mean? That means we're adding an entire New York metropolitan area, 50 million people, every few months. Copenhagen. In less than a week, there'll be another bloody Copenhagen on this planet, equivalently. And in a month, another Denmark. Amazing. Every month now, just continuously. It's fucking nuts. So we live in this faster and exponential expanding socioeconomic universe. So everybody in this room knew, I showed it at the beginning, that we live in an exponentially expanding universe. But most of you probably didn't quite realize that we're living in a faster than exponential socioeconomic universe. That's what's been happening and is continuing to happen as we speak. There it is. You're probably familiar with some version of this. Can I walk with this thing on me? So here's where we began. We were hunter-gatherers. We discovered language, then discovered eventually writing, but we also discovered agriculture. And we learned to make sedentary communities, start to make communities at the beginnings of cities. And everything went beautifully. And you see, by the way, the carrying capacity of the planet for human beings was only about 5 million people back then. But everything went very smoothly till about here, till about this industrial revolution, when we, of course, discovered and learned to exploit fossil fuels, and at the same time developed entrepreneurship, capitalism, free markets, and that has led to all this and to all the marvelous things that we all participate in, and the fantastic quality and standard of life that everybody in this room is privileged to participate in, which has been fantastic. And it's led to this extraordinary growth in the population. Well, if you're a physicist and you look at this graph, I'm sorry, I wanted to show you this too. This is just the various socioeconomic and various material metrics, all following the same way. Things like the GDP and paper production and shrimp agriculture and so on. All of these things, of course, follow the same kind of hockey stick, huge climb. What I wanted to say, if you're a physicist, that graph, any of these graphs, is immediately reminiscent of this. Now, what is this? This is a graph of the heat capacity of propane. What is the heat capacity? It's the amount of heat needed to raise, in this case, 1 kilogram of propane by 1 degree. That's what it is. And it's plotted versus temperature. And what you see is it behaves just like that, the picture of the population. There's a gradual increase, and then at some point it goes completely bonkers. It goes straight up. And if you keep going, you keep increasing the temperature, it goes straight down. And of course, you know what this is. It's changed from a liquid to a gas. And what you're seeing here is what physicists call a phase transition. In popular language, it's called tipping point. But it's actually a singularity. And the singularity, which I will come to shortly, is that this piece here, this piece here is going effectively to infinity, and that's called a singularity. So the question is, by the way, mathematically, this graph is identical to that. They're mathematically indistinguishable. So the question is that just going to follow that? Are we right on the brink of a tipping point where we just crash down? Punkt. This may be the last lecture you'll ever hear. So that's the question I want to address for the rest of the talk. So that fate lies clearly in cities, because that's where all the people are, and I just showed you what's been happening with cities. So what are cities? They're these extraordinary machines that we've invented, that we've developed, maybe the most marvelous machine we've invented, because it's the machine that creates wealth, knowledge, creates innovation, ideas, in order to increase the standard and quality of life for everybody. And it has been enormously successful at doing that. They look like this, and they look like this. This is New York about 120 years ago. Here's more, this is just pictures of cities. But this is the important thing about cities. It's a place for bringing people together, for doing what you're doing here, bringing people together to interact, to create ideas, to create wealth, and so forth. And it's just extraordinary. However, unfortunately, the most fundamental law of science, the one that transcends all laws, is something called, I'm sure many of you are familiar with, the second law of thermodynamics, which says if you do something very positive, something bad will happen, roughly. Meaning that if you create great order in the world, you create new things, you build a cell phone, whatever, you necessarily create somewhere else disorder. And that's called entropy. And we have created both social and physical entropy. This is social entropy. You're all familiar. So inevitably, all this marvelous stuff that we're doing inevitably leads to something like this. It may not be specifically this, where you are, but something of this nature is inevitable. And the question is how to minimize it, because we can't get rid of it. All of this. So that's the question. Is that what it's all going to look like? Is that what Copenhagen will look like? So again, what I said, all of these things that I just showed are all interrelated and interdependent, which makes the problem extraordinarily challenging. But if you ignore the fact that they're all interdependent, if you just consider one problem at a time, we're going to solve this problem, then that we're going to solve traffic here, and then we're going to solve traffic there, and then we're going to solve energy here, and then we're going to solve climate here. If you just consider all of those as separate entities, you run into the problem of unintended consequences. Here's a stupid little cartoon, which I think you'll get immediately, that this is inevitable. And you're all familiar with this kind of phenomenon. So, going back to cities, are they like animals? Are they actually scaled versions of one another? I have to use America. I'll screw up if I use Danish cities. I'll use American cities, is Los Angeles a scaled-down version of New York, even though it looks completely different and so forth. And if they are scaling, is there some universal nature to it as there was in biology? So are there hidden laws of cities, just as there were hidden laws of biology? Well, cities are network systems, as I've emphasized earlier, and so maybe it's not surprising that they might be some scaling laws. So they have not just physical networks, the one I just showed, but there are social networks, and I mentioned this earlier, these kinds of things. And of course, what's going on in that picture is an integration of those two kinds of networks, the physical network of a city and the social network, the information exchange that's going on between people and institutions. And so it's not surprising, therefore, that if you look at infrastructural quantities, and here's some mundane one, this is the number of petrol stations versus size, they scale just like they do in biology, effectively. So what's plotted here is, again, in this logarithmic way, going up by factors of 10, number of gas stations versus population versus population on a logarithmic plot. And what you see, again, is that here it is for four, I don't know if you can read it, it's France, Germany, Netherlands, and Spain, 4 European cities, and they're quite similar. And the slopes, all of them, roughly about, instead of 0.75, 0.85. But it's, again, sublinear, meaning that the bigger you are, you need less gas stations per capita. But what's amazing about this, two things. First, this is true across the globe in terms of if you go to Argentina, if you go to China, if you go to the United States, you go to Australia, you find the same scaling of gas stations versus city size. That's maybe a little mundane, but much more important is that this is true of all infrastructure. The length of the roads, the length of electrical lines, the number of buildings, and so on. All infrastructure across the globe scales just like this, with a slope, roughly speaking, of 0.85. So there's this extraordinary economy of scale. The bigger the city, the greater savings you have in terms of infrastructure. But that's sort of the uninteresting part of a city in a way, because the most interesting part of the city, and the only reason we have cities, is for people to interact through social networks. And how do social networks work? Well, basically A talks to B talks to C talks to D talks back to A, and we build on each other. We're continually having this positive feedback, building on ideas, almost all of which are rubbish and pointless and useless and no one cares about. But amazingly, that very dynamic of interaction of people building on each other leads to the theory of relativity. It leads to an Amazon. It leads to a General Motors. It leads to quantum mechanics and so forth. That's the dynamic that is going on and what cities do. And that leads, instead of sublinear scaling, where you have the bigger you are, you have the less per capita, it leads to what we call superlinear scaling. The bigger you are, the more you have per capita. So the bigger the city, the more interactions, the more of this positive feedback, the more of everything socio-economic. So, and at the same time, instead of a decreasing pace of life, the bigger you are, the pace of life speeds up. It's faster and faster in a systematic way. So here's data on various things. You can't read them, but at the top left is property taxes in Sweden, and in the middle there's divorces, there's restaurants in Holland, there's patents, ideas in the United States, there's crime in Japan, and so on, all of them. But what you can see just by eye, they all look the same, and they all scale in this very simple way. this very simple way, just as they did in biology, except with different exponents, meaning different slopes of those lines. And in fact, almost all of these cluster around 1.15. So, what does that mean in English? I can't say. Says, if you double the size of a city, or you look at a city that's twice the size of another one in the same urban system, then you save approximately 15% on all infrastructure. So all the various things we talked about earlier. And at the same time, you increase all the good stuff like income, wealth, ideas, patents, colleges, and so on. But also all the bad stuff like crime, flu, COVID, and so on, all by about 15%. So there's this, so the bigger the city has this extraordinary, fantastic advantage of getting bigger, that you need to use less infrastructure per capita, but you gain more of social behavior, but some of that social behavior can be bad, and it equal amounts, the bad comes with the good. So a test of that, by the way, is the following, that if you measure social connectivity between people, which we did by looking at using cell phone data, getting billions and billions of cell phone data, to eke out of it the connectivity between people, then that's what you get. And what you see here is the connectivity, again, plotted in the same way versus city size. And it's the two colors there happen to represent Portugal and the United Kingdom. And you can see, as you would predict, since all of those scaling laws came from the interaction between people, the scaling of social connectivity is the same as the 1.15 we saw for all those socio-economic activities. Okay, I'm going to miss that out. So just to show you again, here's the pace of biological life, which I showed earlier, just illustrated by heart rates decreasing with size. And here is walking speed versus population size in a bunch of cities across the world, actually. So the last part I'm going to finish off quite quickly is, can we extend this to the entire globe? That is, can we take these ideas and think of the planet as one unit system? That is, almost as if it's one city. Now, it's obviously highly inhomogeneous. Nevertheless, the amount of globalization that has taken place over the last 50 years, and especially the last 20 years, has been astonishing. If I'd have suggested this 50 years ago or 75, it would be completely nuts. But since then, especially because of the internet, but also because of trade and so on and so forth, the world has become globalized, whether we like it or not. And so let's just explore the idea, maybe it is. And if it is, then if it behaved like a city, it should have scaling. You should see scaling. And you should see this superlinear scaling. That is, the bigger as the planet grows in size, population size, we should have more of everything per capita. But we should see this systematic behavior. If it wasn't globalized, instead of seeing points lining up, roughly speaking, on a line, we would see them all over the place. Okay? So we can test this, and here's the test. There it is. You can see it's not quite as good as the data before. You can see there's kinks and things, and it is bending, but it's pretty, given the crudity of it, it's surprisingly good. So what we see is an approximate superlinear scaling of these are three of the obvious major global net metrics: water use, energy use, and total GDP. And you can see all the exponents, which are called beta there, or the slopes of these are bigger than 1. So just as I say, the bigger it is, you get more. You're getting more energy use per capita, more water per capita, more higher GDP per capita. So I'm now going to try to use that to get some sense of what's going to be happening as we move into the future. So I'm going to use the same idea that I did when I talked about the growth of an organism, the growth of mammals, for example. And so you remember how that went. There was metabolic rate. That's the supply. It goes towards maintaining everything that's here and then adding new stuff. So it maintains all the buildings, maintains all the people, but then you add new stuff, you grow new buildings, you grow new institutions, you have new ideas, you grow new people, and so on. So it's the same, conceptually, it's the same equation, except we have this thing called social metabolic rate now. What's the social metabolic rate? So I want to go back to the biological metabolic rate that I talked of near the beginning. Well, what is that? That's the rate at which energy is used to just keep you doing what you're doing, just sitting there waiting for me to finish. That's called basal metabolic rate. You're in an inactive state. And that's what I plotted here. That's what that was, actually, without naming it. Now, you notice, which I didn't do before, let me go back to that, that you probably didn't look carefully. Some of you may have done at the graph, but if you look across from where you are, you see that's the, shit. There we are, man and woman. If you look across here, we're just less than 100 watts. So sitting there, you're operating at about the level of an old incandescent light bulb. That's all you need to stay alive for the day. 2,000 food calories a day is less than 100 watts. So you're unbelievably efficient, extraordinarily efficient. So there you are. That's what I'm saying. You're a light bulb, basically. Keep that in mind, because I want to introduce the idea of active metabolic rate. So even if you're a hunter-gatherer, you use 100 watts just to stay alive, and you use another 100, 150 watts to hunt and gather. So that's typical. Use about 2 to 3 times your basal rate to stay alive. That's what that is. So, and there are still people on this planet, Borneo, in the Amazon, that operate in their terms of their total metabolic rate, the active metabolic rate, at about 200 to 300 watts. So there it is there. I put on the graph the line of the active metabolic rate. It's 2 to 3 times bigger. But that was how we were. That's how we were 10,000 years ago. And we fit beautifully on that line. And as I say, our cousins who are still hunter-gatherers operate at that rate. No longer true. Because for you to be here, you ought to have clothes on, you have an iPhone, you have a refrigerator at home, you have a road outside, you have cars, you have the whole infrastructure of this city. You carry that with you. That's all part of you. Okay? That's who you are. You're not a bare single person. So, modern human ones, we have to maintain, you are participating in maintaining all of this. So what is that? That number is more like 11,000 watts, 100 times bigger. 100 times bigger, that's what you use, way up there. There it is, up there. So you can ask, how big an animal is each one of you in this room, actually? So there it is, that's what I just said. You're about 30,000 kilograms, each one of you. effectively, in terms of your biological use of energy. Or about a dozen elephants, each one. It's fucking nuts, right? Obviously. So just to put that in perspective, there's now, I guess I should now it's just under 8 billion actually. It's about 8 billion people, close to 8 billion on this planet. But that's totally misleading because if you turn in terms of the energy we use and relate it back to being a biological human being that was a hunter-gatherer, there's actually close to 1 trillion people on this planet. And I have to remind you that when we were all hunter-gatherers, the Earth could only support 5 million human beings. So there it is. So just to remind you, in terms of growth, just to repeat what I said earlier, the demand outstrips the supply in the biosphere, and that's why we stop growing. So we cease, and we have this finite carrying capacity, and that was the graph I showed you earlier, effectively. But now we have the other way around. We have this super linear behavior. Namely, you're getting more per capita the bigger you are, and that completely outstrips the maintenance needs, the demand. So supply completely outstrips demand, which means you have open-ended growth. Instead of growing and stopping, you just keep growing. Demand just keeps outstripping faster and faster the demand. There's a cartoon of it. There it is. And in fact, it leads to something called super-exponential growth, namely growth that's faster than exponential. So this is actually great in a certain sense, because I have a beautiful theory here. I say, okay, we have networks, social networks. We have this positive feedback. Positive feedback leads to superlinear scaling, and superlinear, which we see, and I showed you the data, superlinear scaling leads to super-exponential open-ended growth, which is what we see. Fantastic. We're in great shape. That's what we have. All our cities, our planet, and in fact, that theory can predict these curves. So it's great. So very happy with that. And can produce these. But, and here's the big but, it also leads to something that we technically call a finite time singularity. Now, what does that mean in English? It means that, shit. Sorry. Listen, I'm 85 years old, so bear if I fuck up. So, yeah, so here it is. What it means is this is going up, but in some finite time, I already sort of intimated this at the beginning, this is going to infinity, which is nuts. You can't have GDPs and the number of AIDS cases and patents going to infinity. So obviously there's something crazy here. And the theory tells you what it does. It says not, now here's the big thing. I showed you propane, and I showed you that transition, and the curve was just like this on that side of the singularity. On the other side, it just dropped like a bomb. Well, the good news is it does drop, but it doesn't drop like a bomb. It sort of stagnates and then collapses. So it leads to depopulation, and that's not such good news. That we're approaching a place where we might go through that. So here's the question. How do you stop that happening? Well, if we can click this, we know how we did it. So here's the idea. So you start this growth, but you realize that this is done within some paradigm. That is, we're in the Stone Age, we're in the Bronze Age, the Iron Age, whatever you want, but you call it that because iron in the Iron Age sort of somehow dominated in the same way that today the internet dominates, or before that just computers dominated, or before that coal and steel dominated. But there was a paradigm, something that set sort of a paradigm, a major innovation that sets sort of the background parameters for the way that grows. So that suggests that the way you avoid the inevitable collapse on the other side of it is you intervene beforehand by making another major innovation, a paradigm shift. You reinvent yourself in some way. You invent computers. You discover the internet, whatever. You discover bronze, whatever it is. You do it. And you can start over again, which is great, and keep going. And you'll hit another singularity. And of course, it just keeps going, which is great. But it has a problem, namely that all you're doing is postponing, because another one's going to come along, and furthermore, and this is the kicker, you have to do it faster and faster. So not only does life speed up, but you have to make these resetting, these paradigm shifts, these major innovations faster and faster. So something that may have taken 100 years, 1,000 years ago, now only takes 15 years, and soon it'll only take 10 years, and then 5 years. So you have a sort of reductio ad absurdum argument. This is clearly not a sustainable system. So here's data. I always have to say this. I don't know who this fellow is. I just saw this on the web, and it looked like my work, so I just stole it and showing it to you. I'll be sued one day. I'm going to miss this too. So here's the final thing. The theory predicts, I'm obviously not showing you mathematics, I do have to show you one little equation here. The following, that if this is correct, then you can test it, because it says if you plot the logarithm, again, plotting logarithmically, one of these metrics, energy use of the globe, versus the time to the next singularity, the theory predicts it should just be a straight line. The whole globe just boils down to a straight line. Not only that, the theory predicts the value of that singularity. It predicts all the parameters in this. So here's the data. This is data on energy use up until 1975. And here's what we discovered. You see, it's a straight line. Fits remarkably well, with a caveat. And here's the caveat, that there's two straight lines. And you ask yourself, when was this? Turns out it's about 1970, mid-1970s. So this is, you don't have to believe the theory, you don't have to believe anything I said. This is just data. There's a break. Something happened in the mid-70s. Now, goodness knows what it was. It could have been the great oil crisis, could have been the beginning of globalization, could have been the beginning of the women's movement. Who in the hell knows? Any of these, I don't know. But there it is. There's the data. But the point is, we're heading towards a singularity. One minor technical point I have to tell you is that it's the log of Tc minus T. This is a technical. Time is going the wrong way. In a way, it's going that way. So what I said, so we're heading towards some major singularity, and we have to intervene in some way. So there it is for global water use and so on. So I'm going to finish there, leaving it sort of hanging a little bit. But I just with a couple of remarks. Just to remind you what I said, so we have this, the very thing that has brought us here, our very dynamic, our very fantastic way of bringing people together, creating ideas, creating institutions, and so on and so forth, and has brought us the marvelous society which we're privileged to participate in, actually is our undoing. It's leading us to something that's collapsing, and it's leading us there faster and faster. So it's accelerating. So we have to innovate faster and faster. Secondly, all socioeconomic life is going faster, and yet we have the same brains and the same biology that we did when we started on this journey 10,000 years ago. We have the same brain as a hunter-gatherer of 10,000 years ago or 100,000 years ago, whose life basically didn't change, and ours are changing at this extraordinary rate. And one question that it's begged here is, can we continue to adapt? I said I'm 85. Can you imagine being 85 and having to adapt to another fucking one of these? And to have all these young guys I work with, young men and women, who are continually telling me to use another goddamn app or another whatever when I write papers together. So, we're all reaching a sort of critical point in terms of this problem, this issue, that when are we reaching the critical point in which we're not able to adapt to our own innovations, which is kind of extraordinary because we make it all, but we have to adapt to it. Okay, so that's the question. And we're just like Sisyphus. We're just pushing rocks up the hill and it's falling down again, except now they're accelerating, unfortunately. I want to finish with a couple of things, a quote. I don't know how many of you know who John von Neumann was, the greatest mathematical physicist of the 20th century. You wouldn't be using your computers and your iPhones without von Neumann. He's the man that invented the architecture of modern computation. He invented game theory, which is fundamental in economics. He formalized quantum mechanics and so on and so forth. But in 1953, he made this statement: the ever-accelerating progress of technology gives the appearance of approaching some essential singularity in the history of the race, beyond which human affairs as we know them could not continue. And so what I've tried to do is put a little teeny-weeny bit of flesh on that statement. I don't know what else I've got here. Oh, I have some non-science things to say. Humanity at a crossroads. We have a choice, right? We all know that. We're facing that. It's right now. I'll be dead, but you have to continue. And what we obviously do need is, instead of attacking all these problems piecemeal, we need to have something integrated and together. So we need something that I'd like to call a grand unified theory of sustainability that includes everything together, including the practitioners and the politicians and the scientists and whoever. Everybody needs to be in this to be doing it. And we need to use everything at our thing. And by the way, I have a very skeptical view of AI, even though it would be crucial in this. But that's a whole nother question. And we need a revolutionary change in our mindset because it all comes from us. What do I got? I don't have time to talk about that. These are all the wonderful people that did all the real work. I'm not going to say anything about them. I just want to show pictures of them because they were all wonderful and that we all had fun. That's the main point. And shamelessly advertising my book, which is not in Danish, but it is in Dutch and Swedish and Finnish. I'll finish there. Thank you. Thank you.